Okay, this is Physics 17, Section 1. Got a secret shout out to Sydney. I say secret because since she doesn't watch my videos, she's not going to know that we did the shout out. Alrighty then, we're going to be looking at reflective surfaces. We talked a little bit about this in class, so this hopefully the first part will go pretty quickly. So we're going to be looking at plane mirrors. And we got some essential questions. The law of reflection we talked about. Specular means that you get a good sharp image. Diffuse reflection means that you don't. And then what are the images going to look like and where are they going to be located? And then we're going to do a little bit more math beyond that too. Remember, normal line is perpendicular to the mirror. So we're going to look at some of these new terms. Again, we've talked about these in class a little bit. So again, if you're looking at water, the ripples mean that you're not always going to get a nice clear reflection. If there's no ripples, then you're going to see it real smooth. The Egyptians realized you have to polish a mirror if you want to get a good clean image, but really we didn't get anything, we weren't able to do images really until about 1857 when we were able to start coating glass with silver, and then we started getting some really good mirrors. So again, remember that if the light does not go through it, we say it's opaque. If some of the light is absorbed and the rest it's reflected, light wave travels in 2 dimensions, encounters a barrier. The angle of incident is equal to the angle of reflection, which gives us our law of reflection, which basically just says that angle theta of the incident is going to be equal to angle theta of the reflection. And so you can see here that as the angle changes, as the incident changes, the angle of reflection changes. If we have a bunch of lights coming in parallel, then you're going to see it all coming off at a parallel angle. Again, smooth surface is going to give us a specular reflection, means that we're going to see the image. If it's not smooth, then we get it kind of bouncing off in a bunch of different directions. So rough surface. So light waves make up the beams parallel before they strike surface, but they're not parallel when they come back, so they don't form a good image. We call that diffuse reflection. Now the microscopic scale and normals of the surface location where the rays strike are not parallel. So again, we're not going to see a nice clean image. Okay, we talked about this in class. If we rotate, if we have a incident ray of 52 degrees and we rotate the mirror 35 degrees, what's going to happen to the new reflected rays, and what's the angle between the initial and the final reflected ray? So what was the initial reflected ray and the final reflected ray? So if we sketch our image here, we could see we're changing the mirror by 35 degrees. So now our incident, if this is our ray coming in here, and now this is the ray coming in here, it's obviously going to change from bouncing way down there to bouncing off in this direction. So we're going to change the mirror by quite a bit. Now this is a 35-degree angle. So we know our initial, we know how much we changed the mirror. We're trying to figure out the change in the reflection. So the change in the reflection is what we're looking for. We could solve that. Again, we're rotating clockwise, so we know we're going to reduce the incidence. So if we substitute some numbers in here, we could figure out we just changed the incident by 17 degrees from the new normal. And again, the reflection, if the incident changed by 17 degrees, then the reflected is going to change by 17 degrees. So all we did was we said we changed it by 17 degrees. And so basically then, if we want to figure out how much it's going to change from the original ray, we would take basically this calculation. So it's how much it changed by minus the incident ray, we get 70 degrees. And we did all of our steps, and it looks reasonable, which kind of leads me into where we really want to talk about today, and that is objects in a mirror. So again, we're talking about a specular reflection. We must consider the object of the reflection and the type of image. So we're going to be talking about this idea of image and virtual image. The object then, when we talk about the object, we're defining that as basically being the source of the light rays that are being reflected by the mirrored surface. The object can either be luminous itself or it could be illuminated by another source. Doesn't really matter. The mirror is still going to reflect the rays coming off of here. Here we have an illuminated object. The bird is basically there's a bunch of rays that are going to be coming off of any particular point on the bird. That's all they're trying to say here. And so here, all these rays are coming off, and they're going to strike at some point. Okay. So what's happening to the light? Some of the rays are going to travel from the bird, are actually going to hit the bird. Some of the rays are going to go off in other directions and not hit the mirror. But we're really interested in stuff that hits the mirror. So what does the boy see? Well, the boy's going to see this. He's going to see one of the rays or a series of the rays are going to hit his eyeball. Some of the rays are going to miss him, but some of the rays are going to hit. And so basically he then is seeing, right now he's just looking at this part. He's actually seeing the whole bird in reality, but we're focusing on just the ray that was coming off of here and that he's seeing. So that's what the boy is seeing. You'll notice that the ray is coming straight at him from the mirror. So what does that mean? He's processing the information as if the light's traveling in a straight path. So he's going to see the light that had followed these straight lines. So the light seems to be coming from a point behind the image. What does that look like? So in other words, the ray that he's seeing right here seems to be coming from here. In other words, if he didn't realize he was looking at a mirror, he would think that he's looking at the bird out here. So that's the image point. And so he's going to see the points, and of course he's looking at many points from the same bird. Same thing. So we say that this combination of points is going to create an image of the bird, and we say it's a virtual image because it's not the actual image itself. It's a virtual image formed by all these rays coming off of the mirror. The virtual image is always on the opposite side of the mirror from the object, and images of real objects produced by plane mirrors are always virtual images. If you're looking at yourself in a mirror, you can see that the image appears to be the same distance as you are in front of the mirror. You could also see that your image is oriented so that it matches your size. Now you say, yeah, but wait a minute, if it's smaller, if I'm way far away, yeah, but if you looked at a friend of yours that was your same height standing way down the hallway, and it would look smaller, but it's just because of perspective, really. It's not the person's height is still the same height. And so if you move towards the mirror, the image moves towards the mirror. If you move away, the image moves away. We could look at the geometry behind this. Here we have our object. Here we have our image. Here we have x, the distance of the object from the mirror. Here we have the distance, the perception of a distance of the image from the mirror. We have one ray that goes in and comes straight back. We have another ray that's coming down here and bouncing off at some angle, and so an observer down here would see it at an angle. The object itself, if you were standing right behind the object, it would seem to be coming from here, from the back here. So anyway, so we could basically create ourselves a triangle here. to raise point O at the tip of a candle. This is supposed to be a candle right here. Strikes the mirrors at point 1p, and then the other one is hitting at point 1 p2, I should say. Both rays are reflected in accordance to the light. Reflected rays are extended behind the mirror on the sight line, okay, and they seem to converge at this point I. So if you look at the geometry behind it, ray 1, which strikes the mirror, comes right back 90. It's 90 degrees to the mirror. It's 0 degrees from normal. Ray 2 seems to be coming off of it at the same angle as ray 2 hit the mirror. And so if we look at a little bit of geometry here, we have some line segments. We have this line segment of OP1 and IP1. These line segments are the same. And there's the corresponding sides of two congruent triangles. Again, if you draw a line down where the mirror is at, you could see a triangle over here. We see a congruent triangle on the other side. They share a side, they have common angles. So again, if we look at the length of XO, it has to equal the length of the OP. Well, this is just saying, yeah, XI is IP. And so then basically we could derive the equation saying that they're the same distance, just different. The negative just indicates that we're looking at an image that is virtual. Yeah, this whole negative thing, be careful when you're looking at this negative. Doesn't always mean you're subtracting. Sometimes it just is giving you an indication of where the image is or what the image is doing. So that'll hold true when we start looking at lenses as well. And again, you could draw the triangle, and the sight lines converge at that point. And so again, we could look at the height. The height is again going to be the same. So if we look at a plane mirror produces an image that's the same orientation as the object. However, there's a difference between you and the appearance in the mirror. Okay, so if this kid's looking at himself, sees himself in the mirror, so actually this is the kid, this is the object, so this is a kid that's looking, this is a kid, this is the image. The biggest difference is that the right hand of the boy converges with what appears to be the left hand of the image. So he's extending his right hand. It looks like he's extending his left hand in the image. So we have this mirror image. The left and right appear to be reversed in the mirror plane. So why aren't the top and the bottom reversed? Well, this does not happen because the plane mirror doesn't really reverse left and right. What the mirror really is doing is it reverses the boy's image such that it is facing in the opposite direction as the boy. In other words, it produces what we call a front to back reversal. Okay, so okay, we're almost done. One last thing I want to look at is can we figure out what a full-length mirror would be? That's going to be our challenge in classes. How long does a mirror have to be so that the boy can see his feet, essentially? And so we're going to give a measurement of the distance to the mirror, the height of the boy or the girl in the case of in the class situation. And again, we're going to look at how long the mirror has to be. So start thinking about some of these angles. You're going to have an angle with the floor, and you could create a triangle down here. Consider where the normal is, so what these angles have to be and how they relate to the angle with the floor. And then we're going to have similar triangles, but not necessarily congruent triangles. Well, actually, in this case, we will have congruent triangles. And so just think about what those triangles are going to look like, because that's what we're going to work with. Okay, that's it.